Welcome back to Discrete Differential Geometry. Last time we talked about curves in the smooth setting, and this time we're going to look at the complementary discrete picture. So we're really going to connect the dots. We're going to describe discrete curves as a sequence of points in the plane or in three-dimensional space that we connect by straight line segments. And although this sounds like a very simple elementary object, what we're going to see is it actually captures a lot of the rich structure of curves from differential geometry. And with these simple curves, we're going to be able to do some really interesting things in terms of geometry processing and capturing physical phenomena. So just to recap what we talked about last time, we introduced the idea of a parameterized curve, basically saying that a curve can be viewed as a function or a map that bends an interval of the real line into space. One really important thing that we talked about is that every curve has many possible parameterizations, many different maps that describe the same shape in space. One basic reason why we use parameterized curves often in differential geometry rather than other descriptions of curves is that it becomes very easy to express important local quantities like tangents and normals and binormals and curvatures and torsions in terms of derivatives of this parameterization function. And last time we introduced the idea of the Frenet frame, which kind of ties a bunch of these quantities together. We also made the important distinction between embedded and immersed curves. So embedded meaning that essentially the curve gets mapped into space while preserving its topology. It doesn't cross itself. Its endpoints don't get glued together. Right? An open curve remains open. A closed curve remains closed. An immersion can have self-intersections, but is at least regular. It's nice and regular in the sense that the derivative or the differential of the curve is well defined everywhere. And that's really important because the differential is what lets us express, well, differential quantities like the tangent and normal and curvatures and so forth. We also noticed some very interesting things about curves in the plane, that they have two natural numbers associated with them, one being the turning number, so the degree of the tangent map as we walk around the curve, how many times does the tangent turn around, and the winding number, which for a given point in the plane says, well, how many times does the curve kind of wrap around that point. Finally, we introduced the fundamental theorem of plane curves, which says that you can recover a curve purely from its curvature, up to a rigid motion, or for curves in three-dimensional space, you can recover it from curvature and torsion up to a rigid motion. Actually, we said very, very importantly, this is true if you assume that the curve is arc length parameterized. More generally, the fundamental theorem says a curve is, at its core, defined by its curvatures and its parameterization. So how fast do we move along the curve, and how quickly do we turn as we move at that speed? Okay? So today we're going to re-examine all of these ideas from the discrete point of view. And again, what we're going to see is even simple discrete polygonal curves actually capture a lot of these same ideas in a very natural way. Okay, so what do we mean by a discrete curve? Let's start out, as before, in the plane, where we will define a discrete curve as a piecewise linear parameterized curve. Put more simply, a collection of points, a sequence of points, gamma 0, gamma 1, gamma 2, and so forth, that are connected by straight line segments. Okay? So we can think of this as a continuous map from 0 to L into the plane, or we can just think of it as, well, connecting up the dots. And as shorthand, we'll say that the position assigned to the point S sub I in the interval 0L is going to be called just gamma sub I. As a concrete example, let's say we want to describe this simple curve made of two line segments. Well, we could write it out very explicitly in terms of a parameterization. We could say that gamma of S is, well, for values of S between 0 and 1, it's equal to S0, right? So we stay at height 0 and we just move in the positive x direction. And then once we get to S equals 1, we start moving upward. We keep our x coordinate fixed and we increase our y coordinate. Okay, so the point here is just to say that we can always think of a discrete curve as the image of some continuous map, right? Some continuous deformation of that interval, but it's fairly atypical to write it this way. Normally, we'll just think about these curves as literally connecting the dots, as segments in space. Okay? How can we think about discrete curves in terms of discrete differential forms? We spent a lot of time developing that language. Well, a discrete curve is ultimately determined by a discrete Rn-valued zero form gamma on a manifold and oriented abstract simplicial 1 complex. Okay, so that's some very, very fancy language for describing something as simple as just connecting the dots. But at this point, you should be able to kind of hit pause, read through each of those words, think back to all the discussions we've had, and really untangle that, right? So if I have a simplicial 1 complex, K, that just means I have a list of edges together with all their vertices, and okay, maybe also the empty set if I want to be closed under the operation of taking subsets. And actually, these edges and vertices are not described by unordered sets, but rather ordered sets. V0, then V1, V1, then V2, indicating an orientation along each of these edges. Okay? The zero form, gamma, then gives the location of the vertices. The fact that it's a discrete zero form means I have a single value per vertex, per zero simplex, right? And the fact that it's Rn valued means that these values per vertex aren't just scalars, but they're actually coordinates. They're coordinates in Rn. Well, we don't have to write them in coordinates, but they're at least points in Rn. Okay? And then we said whenever we have a discrete K-form, we can interpolate it to turn it into a continuous K-form by using the so-called Whitney bases. In this case, the Whitney bases are just the hat functions. We just do linear interpolation of these coordinates in order to get these line segments. Okay? This might not be really essential to do for curves, but as we start talking about discrete surfaces, it's going to be really, really nice to be able to connect our language of differential forms with discrete computation. And so curves are a nice warm-up for that activity. Okay, so that's what we want to do. We want to be able to translate statements about smooth curves expressed in terms of smooth exterior calculus into analogous statements about discrete curves using discrete exterior calculus. So a simple but important example of a quantity we care about with curves is the differential, right? To say anything at all in differential geometry, we need to be able to differentiate the geometry. Okay, and our most basic derivative is to take the differential of our map describing the shape. So the differential of a smooth curve, right, do you remember our interpretation of that? The differential of a smooth curve basically says if I have a tangent vector in the domain, right, I have a little arrow that's just pointing along the real axis, it has some magnitude, maybe it points to the right, maybe it points to the left. Then I want to know how does that arrow get stretched out as I bend this interval into the curve in the plane. Okay, so the short black arrow might turn into a slightly longer blue arrow. What is the differential in the discrete case? Okay, so this takes a moment to recall how the differential works, how discrete exterior calculus works, and so forth. But you'll notice we've written the differential as d gamma. If we think of gamma as a zero form, right, then what is the discrete exterior derivative on a zero form? It says, well, I just take differences of values, of zero form values, along edges. Okay? So the discrete differential of our discrete curve is nothing more than the difference of two consecutive vertex positions, or in other words, it's the vector that points along the edge. Okay, so hopefully that's fairly natural. If I integrate the differential along an edge, I get the vector that points along that edge. What about the discrete tangent? So this is an important moment to stop and think, okay, what was the difference between the differential and the tangent. They are kind of similar ideas. They both sort of point along the curve in some way, but what really is the difference? Well, the difference is the tangent is a vector, and the differential is a map that pushes forward vectors. We also said in the smooth setting that when we talk about the tangent, we're really going to talk about the unit tangent, right? So we can more or less normalize the differential to obtain the tangents. On a smooth curve, we might say the unit tangent T of S is what we get by taking a unit vector along the interval 0 to L, pushing it forward by the differential, giving us a vector in three-dimensional space, and then normalizing that to get a unit vector. Okay, same idea here. We just take our discrete differential, these edge vectors, we normalize them, we get the unit tangent. Okay, and I want to emphasize again that we're not simply saying the differential is the non-normalized tangent and the unit tangent is the normalized tangent. No, right? This should be especially clear in the smooth setting. The differential is a map that takes any tangent vector into space. The tangent or unit tangent is a particular tangent vector on the curve. Okay, two different things. One thing that we don't get in this picture is we don't get a clear definition of tangent vectors at vertices. Right? This kind of is starting to sound like a problem we had in our first lecture. Sure, if I have a piecewise linear curve, I can do all the differential geometry I want on the interior of these segments, but what happens at the vertices where things are not differentiable? Well, that's a question we're going to have to keep asking and keep coming up with good answers for. Not just about tangents and differentials, but about other quantities, normals and curvatures, not just about curves, but also about surfaces. Okay? That's kind of part of our core activity here, is to try to figure out what do these differential quantities mean? What is the proper analog of these differential quantities when I can't just plug in the baseline classic definition? Okay? But we can at least keep going here with the normal. Okay, so how did we describe the normal in the smooth setting? We said, well, we could think of it, at least in the plane, as a 90-degree rotation of the tangent. Right? And I have to pick a convention. Do I think about the counterclockwise rotation or the clockwise rotation? Right? But once I've picked this convention, it's not hard to write down the normal. Okay, so then in the discrete case, same story. I have my discrete tangents, just a unit vector associated with each edge. I can rotate those by 90 degrees, counterclockwise, let's say, and I get my unit normals for edges. I still don't have any notion of normals at vertices, right? But I at least know what this means for edges. Okay, and even with this basic data, discrete tangents, discrete normals, I can start thinking about questions like, what does it mean for a discrete curve to be regular? We spent some time talking about that in the smooth setting. In a lot of situations in geometry, you have some kind of regularity condition that says, well, when is a curve nice? When is a surface nice? When is a manifold nice? What are some simplifying assumptions I can make about my geometry that ensure I can talk about them without worrying about all sorts of weird corner cases? Well, in the smooth setting, we said a curve is regular if its differential is non-zero, meaning if non-zero tangent vectors get mapped to non-zero vectors. And this condition helped to avoid all sorts of bad behavior. For one thing, we can't have sharp creases or cusps in the curve where the tangent or the normal is not well defined. But also, remember, we can have perfectly nice, smooth-looking curves, even a perfect circle, that are not regular if the parameterization slows down to 0 at a point. Okay, so that was our basic definition of what it means for a smooth curve to be regular. Now, one thing to remember about this game of discrete differential geometry is that we want to consider lots of different equivalent definitions in the smooth setting and see how they might translate into different inequivalent notions in the discrete setting. So a different characterization that we didn't give before is that a curve is regular if the parameterization is locally injective. Okay, meaning globally, maybe the curve crosses itself, but around any point in the domain, I can find a sufficiently small interval so that if I restrict the parameterization to that little interval, it gets mapped to the plane in a one-to-one fashion. In the smooth setting, it turns out these are equivalent. If I have a locally injective and differentiable parameterization, then it is regular in our original sense and vice versa. Okay? So how should we translate this idea of a regular curve into the discrete setting? Maybe the most straightforward thing is to just take our original definition and stick in the word discrete in a bunch of places. So we could say a discrete curve is discretely regular if its discrete differential is non-zero. What does that mean? We said the discrete differential is essentially just the edge lengths. So in this case, having a non-zero discrete differential will prevent zero edge lengths. That's nice. But it may not take care of other things that we care about, like, let's say, zero angles. Okay, so here's a perfectly good discrete regular curve, I think by any definition, right? I have these vertices gamma 0, gamma 1, gamma 2. All my edge lengths are non-zero. All my angles are non-zero. But what about this curve? So here I'm going to go from gamma 0 to gamma 1, then from gamma 1 straight up to gamma 2. Right? I have a single edge connecting gamma 1 and gamma 2. Okay? And then, importantly, I have another edge going from gamma 2 to gamma 3 that travels back along part of the previous edge. Okay? And then finally, gamma 3 connects to gamma 4 along some new edge. So this satisfies our first definition, this idea that the discrete differential never goes to zero. None of the edge lengths are zero. Okay? But it does have places that are kind of nasty, right? We have this gamma 2 vertex where the angle goes to zero. Now, why would that be a problem? I mean, maybe that's okay. Maybe it's okay for that angle to go to zero. Well, one thing we lose if we accept this first definition is you can imagine now I have a motion of the curve. The vertices of this curve are moving around. And as they move around, actually, without letting any of the edge lengths go to zero, I could change the turning number of the curve. I can let some of these angles go to zero. The curve kind of passes through itself, and the turning number might go from 0 to 1 or 1 to 2 or whatever. So in other words, if we accept this very naive definition of a discrete regular curve, we lose this idea of this Whitney-Graustein theorem. And so if we really want something that nicely captures what's going on in the smooth setting, we need a little bit stronger, a little bit different definition. Okay, so here we just play the usual game and we say, well, there's an equivalent characterization in the smooth setting, which is that the parameterization must be locally injective. Right? So in particular, we can say a regular discrete curve or a discrete immersion is a discrete curve that is a locally injective map. By the way, this is a really, really nice way of defining regularity because it doesn't depend at all on any notion of derivative. Right? I'm simply asking about some property of the map itself, and we'll look at this in more detail in a second. Okay? But the important thing, as we'll see, is that this definition rules out both zero edge lengths and zero angles. It really captures the notion of regularity from the smooth setting in a nice way. Okay, so let's look at this in a little bit more detail. What do we mean exactly about this local injectivity? So remember that a discrete curve can still be viewed as the image of some interval on the real line. Right, so I take this interval between, let's say, S0 and S3, and I map it into the plane like this. Okay, and so just to be clear, we go from gamma 0 to gamma 1 to gamma 2 to gamma 3. Okay, and this curve is not globally injective. There's a point where it crosses itself. Right, and so there are 2 points in the domain that get mapped to the same point in the plane. But if I look at any sufficiently small interval around either of these 2 points, then the restriction of this map gamma to that interval is an injective map. So this little segment on the left gets mapped to just a straight line segment in the plane. similarly for this point on the right. Okay? What's an example of something that's not locally injective? Is it even possible, right? It seems like, okay, I could always restrict to a small interval. Well, actually, no, that's not the case. Right, so let's take a look at a different curve, a new gamma. And this curve is going to go, again, from gamma 0 to gamma 1 to gamma 2, and then back down to gamma 3. So where is the pain point on this curve? Where do things go kind of really wrong? Well, just as on the previous slide, it's at this point gamma 2. Right, at gamma 2, well, first of all, globally, it's definitely not injective. Right, I go along gamma 1 to gamma 2, and then I trace back along that edge as I go down to gamma 3. And even if I restrict myself to some small interval around this point gamma 2, or this point in the domain S2, I'm always retracing my steps. And that's going to be true even as I shrink this smaller and smaller and smaller around S2. So this is an example of a curve that is not locally injective, right? It doesn't satisfy our definition of discrete regularity. And so what we see from this is this notion of local injectivity really rules out both zero lengths and zero angles. Okay, really nice. Another very important quantity that we can associate with our discrete curve is curvature. And in fact, we spent our first lecture talking about a lot of different ways, a lot of different perspectives we can use to get at a definition of discrete curvature. Right? One was the turning angle. So we could say that the curvature of a smooth curve is the rate at which the angle of the tangent changes. If we integrate that change over some small interval, we get a difference of angles. And on a discrete curve, that difference of angle essentially just gives us the exterior angle at a vertex. We also talked about the length variation. So I know in the smooth setting that if I want to increase the length of a curve as quickly as possible, then what I should do is move it in the normal direction with speed proportional to curvature. Well, in the discrete setting, it's not too hard to talk about the gradient of the sum of all the edge lengths, and that gives us some notion of discrete curvature. Very similarly, we said if we offset a smooth curve in the normal direction at unit speed, then the change of length indicates where the curvature is. Right? Flat pieces don't change in length. Curved pieces change a lot in length. We can use that again to infer or define notions of discrete curvature. And finally, we said in the smooth setting, we have the osculating circle. We have the best fit circle at each point. 1 over the radius of that circle gives us the curvature. So on a discrete curve, it's pretty reasonable to think about the circle that, let's say, passes through 3 consecutive vertices, and maybe 1 over the radius of that circle gives us a notion of discrete curvature. And I'm not going to go through all the details here. You're welcome to go back and watch that lecture again to get a refresher. But the takeaway message was that depending on which of these smooth perspectives we started with, we ended up with different discrete notions of curvature. It might seem like we have maybe done something wrong, but actually as we played around with these different notions of discrete curvature, we found that a lot of them end up coinciding. There's only so many natural perspectives that you can come up with that lead to a notion of discrete curvature. Okay? And each of these discrete curvatures has some subset of desirable properties that we care about. And we talked about no free lunch theorems. In general, you can't always get all the things you want all at once. You kind of have to pick and choose which ones are most important to you. That being said, it is also important that all of these notions converge to the same answer as we refine our curves. Right? So if we get a finer and finer curve, at least if we have some reasonable sequence of discrete curves that approaches a smooth one, we should eventually see the same values coming out of all of these. Okay? We didn't talk about that in detail, but that definitely will happen for any reasonable definition of discrete curvature. One big reason why we introduced the idea of curvature in the first place is because of the fundamental theorem of curves. Right? Basically saying that a curve is essentially just described by its curvature up to rigid transformations. And if we pick a particular definition of discrete curvature, we also get a fundamental theorem of discrete plane curves. Okay, so here it is. So, fact, theorem, up to rigid motions, a regular discrete plane curve is uniquely determined by its edge lengths and its turning angles. Okay, so in the discrete case, this theorem should be pretty obvious, right? If we just think about, if I hand you this data, if I hand you the lengths of each of the edges, and I hand you the exterior angles at every vertex, how could you recover the curve? How could you draw this curve on a piece of paper? Think about that for a second. Okay, well, hopefully this is pretty intuitive, right? I could put my pen down, I could move it the distance of the first edge, then I could rotate the direction by the first angle, move the pen by the length of the second edge, and so forth. If I want to be a little more precise about this, I can write this down just like I did in the smooth setting. So rather than integrating the curvatures to get the angles of the tangents, I can just sum the curvatures. So I could say phi sub I comma I plus 1, so an angle associated with a particular edge, is just sum of all of the exterior angles theta, right, leading up to that edge. Okay, so that tells me the direction of the edge relative to, let's say, the horizontal. Okay, if I know the direction of the edge, I can write down its unit tangent by just saying, oh, well, then the unit tangent is just the cosine and the sine of that angle. Okay, once I know the unit tangents of the edge and the edge lengths, well, then I can kind of just build the edges, right? Multiply lengths by unit tangents and add them up. To get the location of the ith vertex, I just add up all the edges that came before it. Okay? Hopefully that feels pretty concrete. Now, there's one thing missing from this story, right? Which is we said that this data determines the curve up to rigid motions. So where do these rigid motions show up in this reconstruction process? Well, two places. Right? For one thing, I need to pick where do I put my pen down to begin with. And so I could put an additional constant in this last sum to say, where's the first endpoint of this curve? Okay. And also the direction. So I have to pick an initial direction to start drawing my curve. That's going to be given by some constant in this first sum, right? To some initial angle, theta naught, plus this sum. Okay? So if you weren't following the fundamental theorem for smooth curves, maybe this makes it clear, right? All we're doing is joining up little segments end to end and rotating them by some angles that we wrote down before. Okay, so that was kind of the most basic theorem that we want to translate from the smooth to the discrete setting. What about other observations and statements we made? Well, maybe you remember this Whitney-Graustein theorem, which says that if two curves have the same turning number, then there's a regular deformation of one curve into the other, right? A curve that always stays regular, that stays immersed. And likewise, if there's a regular deformation or regular homotopy between two curves, that means they must have the same turning number. It's an if and only if. Okay? Well, if we adopt the definition of a discrete regular curve that we've given in these slides, if we say discrete regularity means local injectivity, then there's a discrete version of the Whitney-Graustein theorem that exactly mirrors the smooth one. Okay? And I just want to pause here and make a little bit of a meta point, right? What we're saying here is there are different definitions, different discrete definitions we could adopt, and they have different consequences. In this case, if we say a discrete curve is regular if it's locally injective, then we get a very nice discrete analog of some important theorem. If we had stopped and said, oh, discrete regularity just means edge lengths are non-zero, then we would not have this theorem. Right? And this is the way it's always going to play out. We want to get a sense of which discrete definitions are good or bad or useful or less useful by seeing how many puzzle pieces fit together, how many things that we knew from the smooth setting still hold, are still going on as expected in the discrete setting. Okay, so this particular question of discrete Whitney-Graustein has been carefully studied from several different perspectives. Maybe the first one that I know of is a kind of case analysis showing that this is true. There's maybe more geometric argument using convex polyhedra that came a bit later. But both of these proofs use a central strategy that comes up over and over again in differential geometry, which is to, if you want to find a sort of path that connects two distinct objects, one way to do it is to map them first both to the same canonical object. Right? So rather than trying to directly deform the polygon on the left into the polygon on the right, which might be hard, I can do something maybe easier, which is deform the polygon on the left into a regular hexagon and the polygon on the right into a regular hexagon, and then I just compose those deformations. I go from the left to the hexagon to the right. Okay. Why is it easier in this case to go to the hexagon? Well, I'll let you read the details if you're interested. But that high-level story is one that comes up over and over again in trying to show things are true in differential geometry and also in cooking up algorithms, right? Mapping between different spaces. This is a very, very common strategy. Okay, so we've talked about discrete curves in the plane. Let's talk about some of the interesting things that happen when we go into three-dimensional space. And just to review, in the smooth setting, we had, again, a fundamental theorem for space curves, which says that given the curvature function, kappa of s, and also the torsion function, tau of s, of an arc length parameterized curve, we can recover the curve itself. How do we do that? Well, we said that there are these Frenet equations that explain how the Frenet frame is changing along the curve. Right, so as we walk along the curve at unit speed, the change in the tangent, the normal, and the binormal are related to, well, the tangent and the binormal and the normal themselves, and this little matrix that involves the curvature and the torsion. So I know the curvature and the torsion. I can integrate this equation with respect to arc length to recover the curve up to rigid motions. So for a discrete curve, we're going to have an analogous theorem, right, that we're going to be able to recover a discrete space curve just from its discrete curvature and discrete torsion. But we're going to say it in a slightly different way. Okay? But just to start, let's define what we mean by a discrete space curve. So we'll say a discrete space curve is simply a discrete curve in R3 rather than R2. We're really not changing anything about our definition except the dimension of the vertices of the curve. Right? As before, we'll say gamma sub I is gamma of Si. So for this kind of discrete curve, we have a fundamental theorem again. Okay, how can we discretize the fundamental theorem for space curves? Well, here's one way to do it. People maybe outside of differential geometry might just say, oh, you're going to describe the curve in what are called reduced coordinates. Okay, so what does that mean? It means rather than giving the vertex positions of the curve, we can describe the curve in terms of its edge lengths, right, which we could think of as sort of arc lengths along pieces of the curve. The curvatures, which, as in the plane, are just the exterior angles at vertices, right? So two consecutive edges on a curve, even in three-dimensional space, will still sit in a plane. Right? Two edges always sit in a plane. And so in that plane, I can still measure this exterior angle kappa. Okay. Most interesting is, what is the torsion? Okay, this gets a little bit harder to draw, but as I just said, every pair of consecutive edges sits in a single plane. So then I can think about 3 consecutive edges, maybe gamma 1, gamma 2, gamma 2, gamma 3, and gamma 3, gamma 4. Okay? The first 2 edges define a plane, the next 2 edges define a different plane, and the torsion is going to be the change in the angle of that plane, the angle between the normals of those 2 planes. For that reason, we're going to associate the torsion with edges of the curve. Kind of interesting, right? So you notice we have lengths on edges, curvatures at vertices, torsions at edges. This is also a very common situation with discrete geometry. The natural place to put all the quantities is often not to co-locate them, to put them all in the same place. In order for lots of little theorems and definitions to work out, sometimes you have to put these different quantities at different locations. Okay? So if we do this, if this is our setup, then we have a theorem that says a discrete space curve is determined by this data, the lengths, the curvatures, and the torsions, up to rigid motion. Okay? And you can notice something interesting, something important about this statement, which is the curve is determined, yes, by its curvature and its torsion, but also effectively by its parameterization. Right? We didn't say all the edges are unit length. Right? We don't kind of have a arc length parameterized curve, if you like, but rather we have these lengths that can be variable. Okay, so this comes back to this idea that even in the smooth case, you could think of the fundamental theorem as either saying an arc length parameterized curve is determined by its curvature and torsion, or you could think of the fundamental theorem as saying a curve is determined by its curvature, torsion, and parameterization. Either way. Okay, so that's the statement, but I haven't really told you why it's true. Okay, so we can just play the same game as before. Rather than thinking of this as proving a theorem, we can just think about, how do I do this algorithmically? If I hand you edge lengths, curvatures, and torsions, right? Curvatures again being these exterior angles, torsions being these angles between consecutive planes, and I give you some initial point, some initial tangent, and some initial normal for the first plane, which is really kind of the binormal of my curve, then how do I find the vertex positions gamma sub I? Right? Just think about how I would draw this curve in space. Okay, any ideas? Well, here's one simple algorithm. So for each vertex or each edge of my curve, I could start at the current position. Right? I start out maybe at the first point, and then I just move in the direction of the current tangent, a distance given by the current edge length, okay? Just like I did in the plane. Now I know which plane I'm in because I have this normal, right? And so I can rotate the tangent in plane by my curvature angle kappa. Now I have a new tangent t, and to get the new normal of my plane, kind of the new binormal, I just rotate by the torsion angle tau, which is associated with this edge, and then repeat, right? Now I'm at a new point, I move along the new tangent, I rotate it in plane, I rotate the normal of that plane by the torsion angle, and so on. Really, really simple, and maybe the only piece of this that's not utterly trivial to compute is this rotation. So I've written r of u theta to mean I'm going to rotate around the axis u by an angle theta. One of many possible ways to write this is I could write this as the matrix exponential of the angle theta times, well, not the vector u anymore, but a little 3x3 matrix, skew symmetric matrix, representing this rotation. Okay, I'm just giving this formula out of the blue. Actually, this is a very nice connection to a topic called Lie groups and Lie algebras, which is a really nice kind of differential geometry way of thinking about rotations. Okay, but if you want to implement this, this is all you really need to know. Okay, so when we talked about the fundamental theorem in the smooth case, we said, boy, it's really hard to integrate up curvature data analytically to get a curve. There's very few functions that you can sit down with pen and paper and write out, what this curve looks like based on its curvature or based on its curvature and torsion. In the discrete setting, this is easy, right? We have this little loop and we just plug in data to this loop. Okay, so I could just pick whatever function I want. Let's say I ask that the curvature at the ith vertex is 1 over n. So let's say I'm going to have n points in my curve. And the torsion, the ith torsion, or really the torsion of the edge I plus 1, is going to be n minus I over n. Okay? If I do that and I plug this into my algorithm, can you picture it? Just stop, think, what would this curve look like? Well, maybe you could figure it out, but the beauty of having a computer, the beauty of being able to do this computationally is you just hit go and you draw the curve and you get something that looks like this. Right, so can we make sense of this? We start at the bottom, gamma 0, we go up to the top, gamma n. At the bottom, the curvature is pretty small, right? I over n is a small number. At the top, the curvature is big. So we start turning around faster and faster as we go up the curve, right? And the torsion is kind of the other way. As we go along the curve, the torsion decreases. So we're staying more and more in the plane as we go up and just running around in circles in that plane when we get to the top. Okay? But this is nice because if you want to get some intuition for curvature and torsion, right, this doesn't make any sense to you, well, fine, write some little piece of code, right? You could implement this in any language in the world really easily, and start to plug in different curvature functions and torsion functions and really see what this looks like. Right? And this is much, much easier than writing a solver to solve a coupled system of ordinary differential equations. Well, actually, it is kind of a solver to solve a coupled system of ordinary differential equations in some sense, right? It still approximates the solution to those equations. But with some very, very simple discrete arguments, this becomes just a very nice, clean, simple algorithm. Okay, so we've gone through all this work. What's some other fun things we can do with curves? Well, one is we can talk about what's called curvature flow. So loosely speaking, a curvature flow is a time evolution of a curve or a surface or a manifold driven by, well, some function of its curvature. And these flows show up very naturally all over geometry and physics and so forth. They can model physical elastic rods. So if you have a cable that you use to plug in your computer, they can be used to find shortest curves or what are called geodesics on surfaces, or they might be used to smooth out contours in noisy data. So you can think of the place where black meets white as a planar curve, and then you're going to push this curve around to maybe detect features or eliminate noise or whatever. The basic idea of a curvature flow is that you have some kind of energy, which I'll call E of gamma, that assigns a sort of cost to each curve. So a very simple cost might be, what's the total length of the curve? The longer it is, the bigger this energy gets, the shorter it is, the better. Okay? So if you want to make your curve better and better and better according to this energy, you could, for instance, follow the gradient of this energy. You could integrate a gradient flow, push the curve in the direction that shrinks this energy as quickly as possible. Okay? And we'll look at two very simple examples of curvature flow on curves. One is length shortening flow, kind of what we just described, and the other is elastic flow. Okay? So before saying what these are in particular, I just want to point out that there are often two different paths for discretizing a given gradient flow. In both cases, I start out with some description of this smooth energy. I think of it smooth energy on a smooth curve. So I could first take the gradient of the energy in the smooth setting. Right? This gives me some evolution equation for the curve. The change over time of the curve is equal to some function of the curve. Okay? And then I could discretize any derivatives showing up in that equation. Okay, I have to turn smooth curvature into discrete curvature and so forth. The other direction I could go is I could first discretize the energy itself. Right? I could approximate the smooth length of the curve by a sum of edge lengths. And then I could take the gradient of this discrete energy to get a discrete flow for a way of updating my vertex positions over time. In general, it's important to realize these don't always lead to the same numerical scheme or numerical algorithm. And so this is yet another thing that you can play around with when you're trying to decide, how do I discretize things to try to find a satisfactory solution, right? So we talked about, there's all these different ways of defining curvature or the differential or, whatever. There's also different ways of discretizing these flows. And although I won't really get into it, this is kind of the starting point for a whole subject of what's called discrete geometric mechanics. So if you're trying to write down algorithms that simulate physical behavior, physical processes, this distinction becomes very, very important. One of these paths might do a very good job of conserving important quantities like energy or momentum or whatever, whereas the other might not. Okay? But let's just look at some simple curvature flows. So our first one is length shortening flow, and it looks basically like this. I have a curve in the plane, and as time goes on, it gets shorter and shorter and shorter. And so you notice that in order to get shorter, it kind of has to eliminate wrinkles. Right? I generate a lot of length by going back and forth along this snowflake. To reduce the length, I have to get smoother. Okay, so more precisely, we could say the energy for length shortening flow is nothing more than the total length of the curve. Right? So just integrate over the curve, its derivative, the norm of its derivative. Okay, and we've actually already talked about the gradient of length. When we talked about curvature, we said that the length gradient is the curvature normal. So if we want to move the curve in the direction that decreases length as quickly as possible, we should just move it in the unit normal direction with speed proportional to the curvature. Okay? And so that kind of explains a little bit the behavior of this flow. Now, you noticed something really interesting just happened. Our curve vanished. It went to a point and disappeared. And for closed curves, this length shortening flow has some very interesting and well-known behavior. One is that the center of mass is always preserved. Right? So if I integrate position along the curve and take the average, that's always going to stay in the same place. Curves always flow to what some people call round points. This just means over time it becomes more and more and more circular, but also that circle then starts to shrink until it evaporates into a point. Why does that make sense? Well, maybe just think about, how does this flow behave if I apply it to a curve that's initially a circle? It says move in the normal direction with speed proportional to curvature. Well, if I move in the normal direction, I shrink the circle. The curvature increases, so I start shrinking faster. The curvature increases more, so I start shrinking even faster. And in fact, you can show that you shrink to a point in finite time. Okay? Another beautiful property of this flow is that embedded curves remain embedded. Right? So if I have a curve, I start out with a curve that doesn't cross itself anywhere. It'll do all sorts of interesting things. It'll smooth itself out. All these little bumps will disappear, but it will never cross itself. And that can be a very useful property in algorithms. If I say, this curve actually represents a contour or silhouette of an object, right, and I want to smooth that out, well, that's good news, because a silhouette should never cross itself, right? So I can depend on this fact. I know this is an invariant of my program now, right, that this curve will always still describe a silhouette. Okay? How can we talk about length shortening flow or curve shortening flow in the discrete case? Well, we do the same thing. We say at each moment in time, we want to move the curve in the normal direction with speed proportional to curvature. Okay? And this is, again, going to smooth out the curve, reduce noise, while eventually becoming circular. A discrete version would say, okay, however you do it, you're going to eventually have to replace the time derivative with a difference in time. So instead of ddt of gamma, I have gamma at time step k plus 1 minus gamma at time step k divided by t. Right? So this is like a finite difference approximation of the derivative. Okay. And then I could imagine at this moment I still have a curvature flow that's kind of semi-discrete. It's discrete in time. I'm taking, these big time steps, but the curve itself is still a continuous curve. Okay? So to complete the job, I need to also deal with the right-hand side of this equation. I need to replace this curvature kappa and this normal n with some discrete version. And we looked at many, many different discrete curvatures earlier on. Right? One that would be maybe very natural in this case, if we're talking about length shortening flow, is, hey, maybe I take the gradient of the length. I sum up all the edge lengths, and I take the gradient of that sum with respect to the vertex positions. Okay, and if I do that, I get a flow that looks like this. It's discrete in both space and in time. So finally, something I can really compute with a finite amount of computation. Okay. Our second flow is what I'll call elastic flow. So rather than shrinking length, you could try to reduce the amount that the curve bends, right? If you want to make a curve smoother, you don't necessarily want to make it shorter. You just want the curvature to go down. So a very natural energy here would be to say the energy of a given curve is just the integral over the curve of the square of the curvature. Why might I square the curvature? Well, curvature is a signed quantity. Right? So to make the curve straight, I don't want it to bend to the left or to the right. I just want it to go straight. So please penalize kappa squared. The elastic flow is then the gradient flow on this energy, and it looks something like this. Okay, so I start out with this curve with all sorts of bends in it, and you can see that as this flow progresses, it gradually unbends, and this flow has been sped up so you can really see what happens in this beautiful unrolling behavior. You notice the length isn't shrinking. And also something kind of cool happens here. So we end up with a curve that has turning number 0. Okay, so we didn't make any, irregular motions. The curve never became creased. The differential never went to 0. And so we know by Whitney Graustein, actually, that this final curve, this figure 8, has the same turning number as the initial curve. This kind of duck that we had at the beginning, with all these different loops going back and forth, they must kind of sum to 0. Okay. In general, the minimizers of this energy are called elastic curves or Euler elastica, and they really model like real elastic strips. So if you have strips of paper, or strips of wood, or whatever, this does a really good job of capturing the real physical shape of those objects. In the discrete case, we can express this energy using the turning angles. Right? So just sum up, well, not quite just the sum of the angles squared, but we need to remember that this turning angle represents the integrated curvature. It's the integral of curvature over some segment to the left and to the right of the vertex. Okay, so to get a good notion of this energy for discrete curve, we're also going to have to put length into the mix. Okay. One thing I should say, we haven't talked much about convergence in this class, but this is a case where the simple thing, the natural thing that you'd expect, really does converge to smooth solutions under refinement. Right? So you might wonder, is this discrete stuff really telling me something about physical reality, or is it just something that makes nice pictures? No, actually, if you make a finer and finer curve and use this kind of energy, you will get shapes that really look like real physical Euler elastica. A different way we could think about smoothing out a curve is to think about the fundamental theorem of discrete plane curves. Rather than trying to take a gradient of this energy with respect to the vertex positions, which sounds pretty complicated to do, you could say, look, I just want to make the curve smoother. I know the angles, and I know how to reconstruct the curve from the angles. So if I want to make the curvature smaller, why don't I just shrink the angles? Right? For any smaller angles, I can then go ahead and run my little algorithm to recover this smoothed out curve. Very, very simple. Gives you something that's very numerically stable and also exactly preserves the lengths of the edges. One challenge here is the question of integrability. So the fundamental theorem for discrete plane curves says I can recover an open curve from its curvatures and edge lengths, But it doesn't say anything about closed curves. It doesn't guarantee that if I give you a completely arbitrary list of lengths and angles, that those will actually close up into a closed polygon, right? And so if I start to try to smooth out my curve by just shrinking these angles willy-nilly, well, then I shouldn't expect that it closes back up again. Right? So I actually have to think carefully, what are the conditions on angles and lengths that ensure the curve remains closed, and how do I shrink these angles while remaining closed? And this is just the very first of an enormous number of questions in differential geometry about integrability. When does given data actually describe geometry? When do curvatures describe a curve? When do curvatures and other data describe a surface? Right? Really, really important question in geometry. Going beyond the purely geometric context, there are physical problems that we can study using discrete curves. So one is the question of how elastic rods behave. Again, an elastic rod would be something like the cable on your computer, or maybe a strand of hair. Right? So if you want to simulate or model the behavior of such rods, one thing you could do is try to minimize both the curvature and the torsion and kind of keep track of how this curve evolves over time. In this case, to really make this physical, you'll also need to incorporate some notion of momentum. Right? The curve wants to keep moving along the direction it's been moving, but then it has these forces, these curvatures and torsions that are pulling it in different directions. Okay. Both the curvature and the torsion measure some notion of non-straightness, so the curve or the rod is going to try to straighten out and untwist. And even using these very simple, discrete kind of curvatures and torsions, you get a very, very rich and very predictive model of elastic rods. It's actually quite surprising how much rich physical behavior can come out of this extremely simple kind of polygonal model of a curve. Right? You don't need to go into finite element analysis and higher order curves and so forth. Right? Really, just these polylines will do the trick. And there's lots of interesting applications of this discrete elastic rod idea to simulating hair or laying cables on the ocean floor. You can also turn this elastic rod model into a model of what are called viscous threads. So if instead of minimizing the integral of curvature, we minimize the integral of the change in curvature over time, or kind of in mechanical terms, if instead of talking about strain, we talk about strain rate, then actually this same machinery lets us model things like, drizzling this honey onto a surface. And again, it's really quite surprising how simple polygonal models, simple discrete differential geometry, can capture some very rich physical behavior in a very predictive way. So what you're looking at here is this honey being drizzled onto a conveyor belt. This movie on the bottom is a simulation, but the gray image at the top is a real laboratory experiment. And what you find is that as you make this belt go faster and faster, or slower and slower, you get different coiling and buckling behavior. Right? So you might just meander back and forth, or make little loops, or make big loops or zigzags, and that this discrete model actually matches the physical prediction quite well. Right? Again, just with simple discrete curvatures and torsions. Another nice example is untangling knots. So there's this unknot problem that we talked about when we talked about curves, which is that if I give you a curve that's wound around in some way in space, is this curve knotted, or could I untangle it without it passing through itself, without breaking the curve, into just a nice round circle? So how do I figure this out? Well, actually, this unknot problem is still a challenging computational problem. Nobody really knows kind of what complexity class this problem is in. But one thing I can do with differential geometry is I can at least try to see if it's unknotted by minimizing an energy that penalizes not only bending of the curve, so not just kind of the curvature, but also self-collision. So this curve really wants to remain embedded rather than immersed. So how can I do this? Well, I can write down a different energy for my curve, where I imagine that there are kind of charges distributed along this curve. Let's say negative charges, electrons, all along this curve, and they want to repel each other. So when I start out, I think, okay, how do I measure this repulsion? Maybe I do 1 over the distance between 2 points squared. Right? These points become closer and closer and closer together. This energy is going to go up and up and up and up. Right? And so curves that nearly cross themselves are going to be considered very, very bad or very expensive. If I do gradient flow on this energy, it's going to want to push this curve away from itself. There is, however, a problem, which is, what about 2 curves that are just near each other along the curve? Right? So let's say s and t in this integral are just 2 very, very close parameters. Well, there's no way for these points to really move away from each other, right? Unless I kind of keep stretching this curve bigger and bigger and bigger. And so this integral is going to blow up. It doesn't actually mean anything. So what I can do instead is I can kind of regularize it. I can subtract a term that says, okay, push 2 points away from each other if they're close in space but distant along the curve, but don't bother if they're close in space and close along the curve. So if the parameters s and t are similar, don't worry about it. I do that by subtracting 1 over d of st, which really means just s minus t norm squared. And that gives me something called the Mobius energy. Okay? So if I now plug this Mobius energy in, I discretize it, I take the gradient, I get things like this. So here are just 2 kind of very interesting looking curves in space. Let's see, are they unknotted or can I untangle them? And in fact, if I let this run long enough, I see that they both actually do go to a nice round circle. Hard to tell from the beginning, but it eventually happens. Now, just to be clear, this curve is not guaranteed to go to the smoothest curve, right? We might try to untangle it with this energy. It might still get stuck in some local minimum of this energy. So it's not providing any kind of proof, right? But it gives us some concrete way to try to untangle curves. We can then take this kind of energy and run with it. So there's other types of repulsive energies rather than Mobius energy. There's something called the tangent point energy. And if we integrate this energy with various kinds of constraints, like maybe the curve is constrained to sit on a surface or it's constrained to live inside a volume, we can start using this for all sorts of computational design problems, packing a curve into a volume, right? Or tracing out kind of a space-filling curve on a surface, or maybe we want to do graph layout. Right? We want to lay out a big graph in the plane. Well, if we could bend the edges while keeping them from intersecting each other, we could get some very nice layout, and so on. Finally, another kind of physical example, which is modeling the behavior of vortex filaments. So very roughly speaking, a vortex filament in a fluid is a curve along which the fluid is spinning around really, really fast. And vorticity just means kind of spinning of the fluid. It's the curl of the velocity field. And these vortex filaments and vortex rings model things that you might have seen, like somebody blowing a smoke ring when they smoke a cigarette, or a bubble ring that a dolphin might play with in the ocean. This seemingly complicated behavior of vortices spinning around in a fluid has a beautifully simple mathematical model, something called Hashimoto flow. And all it says is that the center line of this vortex filament, gamma, is going to change over time according to just the cross product of the first derivative and the second derivative of the curve. This is assuming that the curve is arc length parameterized. Okay, so now that you know a little bit about curves and curvature and so forth, you should immediately say, well, if I'm arc length parameterized, then the first derivative is just the unit tangent, and the second derivative is the curvature times the normal. Okay, and moreover, what is the tangent times the normal? Okay, this is your Frenet frame. The tangent times the normal is the binormal, so in fact all we're saying is, over time, the curve moves in the direction of the binormal with speed proportional to the curvature. Okay, so really simple example. Let's say I have a circle in three-dimensional space. Can you imagine what happens to this circle under this Hashimoto flow? So I have this circle made of smoke. How is it going to evolve over time? Okay, well, one obvious thing about a circle is it has constant curvature, right? It's symmetric, so the curvature is the same at every point. And what about the binormal? Where does the binormal point? Well, the tangent goes along the circle. The normal is the change in the tangent. right? So it's also going to be in the plane of the circle. And if I take the cross product of two vectors that are in the plane of the circle, they're going to stick out of the plane of the circle. So all this is saying is a circular vortex filament is just going to translate in time. And the speed of translation is going to be proportional to its curvature. Think about that the next time you see, somebody blowing smoke rings. Do small smoke rings travel faster? Do big ones travel slower? You can also get these vortex ring guns, just a little plastic toy where you kind of pull back and with some spring action, it generates a vortex ring. Right, so you can shoot this at your friend sitting across the room, and these things are extremely stable. So even if you're on a completely different side of the room, they'll get hit in the face with this puff of air. Okay. To make this more interesting, we can do it for non-circular curves. This is the beauty of computation. How can we turn this into a discrete flow? Well, we know now how to talk about things like discrete binormals and discrete curvatures, just as we've done earlier in this lecture. And we know how to take explicit time steps, just as we did with our curve shortening flow. If we plug this all in, we get an animation that looks like this. So I started out, in this case, with a curve that isn't circular. And you get this kind of translation behavior, right, that we talked about for the circle. I'm going from the back to the front. But because I have some other interesting curvature to begin with, I get this kind of fun oscillatory behavior. This Hashimoto flow is another example of some very deep ideas in discrete differential geometry. So this is a very simple discretization that I'm showing here, but there are much more sophisticated discretizations via special transformations that exactly preserve invariance of this smooth flow. Again, you can think in physical systems, you have conservation of energy, conservation of momentum, and so forth, and these discrete smoke ring flows also have very natural discrete invariance. This Hashimoto flow and discrete Hashimoto flow also have very deep connections to the area of integrable systems and discrete integrable systems. So this is kind of an adjacent topic of sort of discrete geometric mechanics. Okay, finally, we can, as we've done with some of these other models, enrich this basic vortex filament model with additional information. So you could say, well, these filaments or these bubble rings or these smoke rings actually have some kind of thickness in nature, right? They're not just uniform thickness everywhere. And so if you add maybe additional variables to your equation, the radius of this center line, you can start modeling all sorts of beautiful behavior. So this is showing the comparison between a real video on the upper left and a simulation on the upper right of two bubble rings that are not only moving around and interacting, but also merging and splitting. And you get some extremely good predictions of these behaviors. And on the bottom right, you have these sort of ink chandeliers. You can imagine you drop just a little droplet of ink into water and let it fall under gravity. How does it change over time? Well, actually, it has some very rich and interesting behavior, which you can model. You'd think maybe I have to do some full three-dimensional volumetric simulation. Well, no, actually, if you pick the right discrete model, you can do this just with a discrete curve and a radius function that matches, again, very, very well empirical observations. Okay, so that's it for discrete curves. Hopefully you had some fun seeing all the different things you can do once you've mastered discrete curvatures and torsions and so forth. And next time we're going to start talking about surfaces. Talk to you then.